Hello. All right. Okay, so a few people have joined. Excellent. Now we can start. So, so yeah, unfortunately Toby couldn't make it today. He's busy, but he's passed me on the questions he'd like to go through with you. So, it's going to be me. Today is the final webinar of COMPOS for year 13. So it's the final webinar for you, for all of you guys. Except I think someone is doing both programs at the same time, year 12 and year 13. So maybe they'll see me in year 12 webinars, which you're welcome to join if you wish. But it is the final year 13 webinar. Then I hope you enjoyed COMPOS. We'll send you some. Well, I think we've already sent you a questionnaire. Please provide your feedback and say how you found the course. And of course, we would like to hear where you went on when you finished COMPOS, or which university you went to. We would like to know that. We would like to know of your successes. So yeah, that is that. So let's do some thermodynamics. Thermodynamics is really probably one of my favorite topics, and because it's so unusual when I stumbled into thermodynamics, especially the second law of thermodynamics, which basically says that the amount of disorder in the universe always increases, which is quite cool. I was wondering why my room was always getting messier and messier, and the answer was in the second law of thermodynamics, because entropy increases. So let me share my screen, and we'll go through some questions. Right, specific heat capacity. Specific heat capacity depend. Specific heat capacity depends on what happens to the gas as it is heated. If the volume is held fixed as the gas is heated, then the thermal heat capacity, the heat capacity is CV. And if the pressure is held fixed, the capacity is Cp. Why do you think Cp is greater than Cv? Do you understand what I mean when I say Cp and Cv? Please type in the chat. Do you understand what Cv and Cp mean? And it's okay not to. Heat capacity with constant volume and heat capacity with constant pressure. Yeah, so heat capacity, well, let's look at what is heat capacity. So heat capacity, C is how much heat you need to put into the system for a change in temperature, delta T. And there are two types of heat capacity. There's the heat capacity at constant pressure, at constant volume, and heat capacity at constant pressure. So you can imagine a cylinder of gas under a piston. So this is a piston. And there's some gas particles inside. So there are gas particles inside. If you apply heat to this gas, the gas will heat up. But depending on whether you're allowed the piston to move, it will be a different value for the C heat capacity. So piston is fixed. The specific heat capacity CV, heat capacity at constant volume. And if the piston can move, that means when you heat the gas will expand as well. It will get hotter, but it will expand. Then it is CP at constant pressure. Why the pressure is constant? Well, because if the piston has a if the piston has a mass m, then the weight, the pressure inside, there's P atmospheric. Well, you don't. Oh, you don't really need. You can say that it is a light piston. So you can say that P pressure of the gas is equal to atmospheric pressure. So that's why it's constant, right? Because if the pressure inside was, it's the number of moles. Number of moles, just N. Yeah, ignore the kg. All right. So if you just when we say specific heat capacity, we usually mean 1 kilogram. So N1 kg is the number of moles in a kilogram of gas. But you don't need to worry about that. So what we have here, piston is I'll remind you of the first law of thermodynamics. So first law of thermodynamics. Is the energy supplied to the gas is used to increase. So if you supply heat to the gas, right? So if you add heat to the gas, is used to increase the internal energy, the change in the thermal energy of the gas, plus the work done by the gas. This is the first law of thermodynamics. The energy supplied to the gas, so it's basically conservation of energy, isn't it? You supply heat to the gas, and this heat is used to increase the internal energy of the gas plus do some work. And in this case, you supply this, let's say piston is fixed, then you're supplying the gas only to increase the internal energy. But if you're keeping the pressure constant, you're supplying heat, the increases, the internal energy increases, but also the gas is doing work as well. Gas does no work. Gas does work. So for the same amount of heat, which situation, one or two, one fixed or movable, will create a greater change in temperature. For the same amount of heat, which situation will produce a greater change in temperature? Fixed or not fixed? Let's check your understanding. Answer in the chat, please. Yes, the fixed, less temperature increase. Exactly. The here, the fixed piston will create a greater temperature increase. Okay, therefore, C is greater Q divided by delta T. So because the greater temperature increase, because the temperature increase is greater for CP, so let's call it CP, P, and CV is Q over delta TV. Because delta TV is greater than delta TP, that means that CP is greater than CV. You can also think of it as the gas at constant pressure has a greater capacity at absorbing heat because it uses some of the heat to do work. Okay, so let's have a look. Fit gases. I forgot to test this beforehand, but hopefully that will work. So let's add some gas. This is a nice simulation. Okay, so this is a gas. Pressure is 34 atmospheres, roughly. Okay. That won't work, but anyways. Let's keep the pressure constant. When I heat the gas, you can see that it expands. Okay, so let's see if I can cool it down. Cool it down. So let's keep the pressure constant, 43 atmospheres. When I heat it up, 1, 2, 3. It takes about 3 seconds to increase by 100 degrees. And if I keep the volume constant, cool it down to 200. Okay, so roughly a fair test. So 1, 2, 3, it will take 4 seconds to increase by 100 degrees. So that's like an anecdotal evidence. But you can try doing it, assuming the amount of heat supplied is the same. But yeah, that's the idea. So if you keep the pressure constant, the gas will expand, and you won't see as much heat, as much temperature increase. So that's what we are doing. Show that for an ideal gas, Cp equals Cv plus R. So Cp, if you Cp, well, we're going to write the first law of thermodynamics. So the change in U is equal to dq plus dw. In this case, this is the work done on the gas. And this is the most confusing part, work done on gas. Now we know that we keep the volume constant, the thermal heat capacity is just the same heat capacity as normal, right? Because it's the same as if it was a rigid body. So du is going to be Cv dt. Is the heat capacity at constant volume times the change in temperature, equals dq, and the work because the gas is expanding, the work on the gas is going to be negative. And we know that the work is pressure times dV. Okay. Just a second. Now, if we keep the pressure fixed, then if E is fixed, then we can have Cp multiplied by change in temperature, and that would make it dq. And yeah, so now if we refer to the ideal gas law, so PV equals nRT, and from here we can find the volume, which is nRT over P. Right, and if we find the derivative of dV versus dt, so at constant, assuming the pressure is constant, we differentiate V with respect to T, that will make it NR NR over P. Or in other words, dV equals NR over P dt. Okay. And now, putting everything back into into the system. So what we did is we expressed each term in terms of dt. So we have this, we have this, and all we need is to put that into here. Okay. So CV dt equals dq, which is dq is cp dt minus pdv edv. So it's p multiplied by nr over p times dt. dt cancels, p cancels, and we have cv equals cp minus nr. Or in other words, cp is equal to cv plus nr. So this is for n moles. And if you do for molar, it's small cp equals small cv plus r. And this is for 1 mole. And this is known as molar. cp is molar heat capacity. It's cv and cv as well. It won't be. It will be obvious from the context if we're talking per mole or if we're talking for the whole gas. So this is for the whole gas and moles, and this is for. Does that make sense? How to do this? Okay. And we know that for a just a second. Yeah, we know the values for CP and CV for gases. Okay. And we can see that CV and CP indeed are different by R exactly. Yeah, because if you do 3/2R plus R, that makes 5/2R. And this is to do, 5/2R. And this is to do with the number of degrees of freedom. And I think you were discussing with Toby, just a quick reminder. So if you have a monoatomic gas, a single molecule, it has 3 degrees of freedom. Hence, it's 3/2. That's 3 degrees of freedom. Because it can move left, right, up, down, and into the page and out of the page, right? So it can move. If you think of a molecule, it can move like this, it can move like this, and it can move like this in 3 dimensions, right? A diatomic molecule, diatomic gas. So you have, it looks like this. It has 3 degrees of freedom, so it can move back and forth. It can move left and right, up and down, and it can also rotate in two different planes. It can rotate like this, and it can rotate like this. So you can imagine it has 2 degrees of rotational freedom. So I'm going to take my toy train. This is a model of a. Oh no, I have two model trains. It can move like this. It can move like this. It can move like this. It can spin like this, and it can spin like this. Now, it can also spin like this. But because the mass is so close to the axis of rotation, we don't consider the energy of that rotation is very, very small. So the energy of this rotation doesn't matter. So it's only 5, not 6 degrees of rotation. There is another one. There's another degree of freedom, which is the vibrational, which goes like this. But for small temperatures, that is insignificant. Okay, so this is only significant for very high temperatures. That's why we say that it's 5, not 6. So if we considered the vibrational one, that would be 6. So 5 degrees of freedom. And that's why it's the diatomic molecule. Does that make sense? Okay, lovely. Okay, right. So diatomic, multiatomic. Well, multiatomic is just 6 degrees of freedom because if it's that means it can rotate in 3 dimensions. Lovely. Consider the following setup. 100 milliliters of water is heated and turned into steam at 100 degrees. The top of the piston can slide so that it is kept at atmospheric pressure. How much work is done by the steam? So basically, it is atmospheric pressure. We have discussed the phase change, but that doesn't really matter. Volume of the water is negligible. So 100 milliliters is very small compared to the amount of heat it produces, right? So imagine if you go if you're in a sauna and you splash a cup of water onto the hot stones. The amount of steam produced, or the amount of water, the volume of the water is negligible compared to the volume of the steam produced, right? And yeah, so I think I was in a sauna once where you throw water onto the stones, you had to hold the door. So there was a special person that would hold the door in the steam room, because when you throw water onto the hot stones, the steam produced increases the pressure inside the room so much that the door flings open. It was really cool. It was really cool to watch. There's a special person to hold the door, and you can't make the door open inwards because that would not be safe. The door always has to open outwards because if you need to run out, it can't obstruct you. So yeah, so you throw the water in the stones. There was such an increase in pressure inside the chamber that they had to hold it. That was fun. Anyways, 100 milliliters of water. So what happens is, so the water is negligible. The 100 milliliters is negligible. It is heated and turned into steam. So basically, we need to find the volume of the steam produced. Yeah, do you agree with that? Because we know the pressure, atmospheric. We know the molar mass, so we can find the number of moles. So let's start with finding the number of moles. N is mass of the water divided by the molar mass of the water, which is 100 grams, because we know 100 milliliters is 100 grams. And divided by 18 grams per mole. So that would be roughly 5 point something. 5.5, is it? It's here it is. Sorry, 100 divided by 18. 5.5, 5.6 moles of water. And we need to find the final volume because the volume increases from 0 to V max. V max is when all the water has turned into steam, so now it is a gas. So PV max is nRT, and we know it's 100 degrees. So this is going to be V max is equal to nRT divided by P. Okay, and this is 5.6 times 8.31 times 100 degrees, which is 373, divided by the pressure, so 10 to the 5 pascals. Okay, and that would give us somewhere 17-ish thousand. 5.6 times 31 times 373. Oh no, that's not it. That can't be true. 17,000. 0.0173 736 cubic meters, and the work is pressure times the change in volume. Because the pressure is constant, we're allowed to use this formula. So it is 10 to the power 5 times 0.1736, which makes it 1.74 times 10 to the 4 joules. That's the work done by the gas. So you can imagine that this amount of work can easily open a door, even a very heavy one. Yeah, so that's quite cool. Have you discussed adiabatic? Have you discussed the different types of processes in the previous webinar? Okay, there are different processes. Like a process can be drawn on a diagram, and what's how it works. The ideal gas, ideal gas processes. If you draw a pressure versus temperature diagram, pressure versus volume, pressure versus volume. There are different types. So there are three main properties. So PV equals nRT. That's the ideal gas law, of course. So processes. There is the isobaric process that is at constant pressure. So this is the equation of state. We call it the equation of state. So on the diagram, on the PV diagram, we can say the gas is in state 1. Gas is in state 1. How would an isobaric process look on this diagram if it's a constant pressure? So something changes horizontal line. So this would be isobaric process. So 1, 2, 1, 2 is an isobaric process. The second type of process is isochoric. Isochoric at constant volume. So this is 1, 3. So this process happens at constant volume. It's isochoric cooling in this case. Isochoric cooling, because obviously the gas cools down, because if the pressure drops, that means that it's cooling down. There is another process called isothermic process. Isothermic. Let's call it 4. 1, 4. Isothermic at constant temperature. And the fourth type of process is adiabatic process. Adiabatic. Adiabatic process looks similar to isothermic, but it is steeper. So like this. 5. Adiabatic. So 1, 5 is adiabatic. Now, adiabatic process means with no heat exchange. With no heat exchange. And that means Q is 0. Isothermic process means that the temperature of the gas does not change, and the internal energy of a gas is determined by the temperature. So this is where, at constant temperature, this is where delta U is 0. Because the internal energy of the gas cannot change because the temperature does not change. So this is P equals constant. This is T equals constant. This is V equals constant. And this is Q equals 0. At constant volume, if it's a constant volume, that means that the work done is 0, because work is pressure times change in volume, right? So the work is 0. And isobaric at constant pressure, well, it's just constant pressure. Nothing is really constant is an isobaric pressure except pressure. So P equals constant. Okay. Okay. But you don't have to draw pressure versus volume. You can draw pressure versus temperature, for example. For a PT diagram. And here, these processes would look differently. So pressure, temperature. So P 1,4 is going to be the easiest. So 1,4 is an increase in temperature. It's constant temperature, but the pressure decreases. So 1,4 will look like this. 1,4 will look like this, because we are reducing the pressure, keeping the temperature constant. Okay. Now, if you have the pressure is constant, oh, it's the same. You are increasing, so 1, 2 will look the same. 1, 2 will look the same. 1,3. 1,3 is constant volume. Constant volume. But if the volume is constant, if V is constant, then PV equals nRT. So P is proportional to temperature, isn't it? So if P has to be proportional to temperature, so it would be along this line. So 1,3 will look like this. One, three. So there's a question. I thought internal energy includes both the potential energies and kinetic energies, where only EK, the kinetic energy corresponds to temperature. So the isothermic one is just the change in state of the system with latent heat. So there's still a change in U. All right, so we're talking about an ideal gas. And ideal gas only has kinetic energy. It doesn't have, the molecules do not have any potential energy. That's why delta U is 0, because we're talking about ideal gases. If we're not talking about ideal gases, then it's a whole different story. And the equation of state doesn't apply either. The equation of state of an ideal gas is not applicable to real gases. Well, it is only applicable to real gases at high pressure, low density. Okay. Right, so because pressure is proportional to temperature, it has to be a straight line through the origin. 1,5, well, we're going to a lower temperature. I don't think we can draw PT. Well, the adiabatic process is PV gamma is constant, and so nRT. The pressure decreases. So if you compress a gas, the temperature increases. So 1,5. So in this process, it's an adiabatic compression. When you compress a gas quickly without a heat exchange, without it giving enough time for a heat exchange, if you compress the gas quickly, the volume. Oh, sorry, no, you're expanding the gas. It's so silly. You're expanding the gas. It's in the pressure drops, the gas expands. So it's going to be similar to 1,4 between 1,3. Yeah, so it's going to be roughly like this. I don't think I can draw an exact line, just a rough one, and it's not going to be straight like this. 5. Like you will never be asked to draw an adiabatic process on a PT diagram, so don't worry about it. Now, you can also draw these processes on a VT diagram. Okay, so if you have VT, if the process is at constant volume, it's going to go like this. The process is a constant temperature, it's going to go like this. So let's label these. So that's 1 constant volume, that's 1,3. Constant temperature, that's 1,4. No, the volume is increasing. Okay, so it's the other way around. So you go up. 1,4 is up. Now 1,3 is the wrong way around, I think, as well. 1,3. Because the pressure drops. Why does the pressure drop? The pressure drops because the temperature drops, of course. So this goes the other way. Okay. Then the number 2. Number 2 is constant pressure. Now, if the pressure is constant, and PV equals nRT, that means volume is proportional to temperature, right? Because this is constant. Volume is proportional to temperature. And that means you need it's going to be on a straight line. Now we need 1, 2. Is the volume increasing or decreasing? The volume is increasing. Therefore, 1, 2 is going to go this way. 1, 2. Okay, and the adiabatic process, and it is an adiabatic expansion. So the volume is increasing, the temperature is decreasing. So that is going to go, volume is increasing, temperature is decreasing. So something like this. 5. Once again, you won't need to draw an adiabatic process. So there are 4 main processes that you need to be familiar with: isobaric, isochoric, isothermic, adiabatic. And yeah, and let's have a look at this process. AB is an adiabatic process. Is where there's no heat transfer, and therefore all change in internal energy comes from the work. So what would be an example of any adiabatic process? If you compress a gas really quickly with no heat exchange, well, like this, let's cool it down. Okay, so you have a temperature 145 and the pressure is 10 atmospheres. And if I compress the gas really quickly, the pressure increases. For some reason, the temperature doesn't increase, but this is wrong. This is wrong. This is a problem of this. This is a problem of this model. The model is not perfect. I have a question for you. Do you know why, when I compress a gas, the temperature increases? And that's a profound question. So if you take a piston, if you move the piston this way, compressing a gas, increases the temperature. Unless we cool it at the same time. Same time. Ideas. Why? Why does pressing a gas increase? Don't mind my grammar. Do you have an understanding? And you see this all the time, right? You've studied astronomy at GCSE. When a star collapses, when a red star collapses, it becomes a white dwarf. So it gets hotter. Or when a nebula becomes a star, it collapses. It's gas. It becomes hot. Why? There are three different explanations here, but yes, Andre, that is correct. Particle rebounds with a higher speed. Let's see why. Imagine you are sitting on the piston. You are the piston. Imagine sitting on the piston. In a high pressured system, that pressure has increased the work into that system, so the particles will gain kinetic energies. Versus exerted force. Well, in high pressure. Yeah, I mean, you do work. When you compress the gas, you do work on the gas, right? So the temperature will increase because you've done work on it. That makes sense. That makes sense. But on a molecular level, it's really exciting. So if you think about it, so let's say the piston is moving with velocity u, and a molecule is traveling towards the piston with velocity v. Now, if you're sitting on the piston in the frame of reference of the piston, you are stationary. Stationary in your reference frame. And what is the velocity of the molecule in your reference frame? U plus v. Thank you. U plus v. In the same reference frame, because it's flying towards you at speed v plus u, it will rebound with the speed v plus u, u plus v. It rebounds with the same speed, because duh, it does. It's an elastic collision. Now, in the frame of reference, in the stationary frame of reference, in the stationary frame of reference, the piston is still moving at velocity u. The molecule is moving with velocity v, but it is rebounding because it's moving u plus v, but since that's in the frame of reference of the piston, which is moving, therefore, relative to a stationary observer, this will be moving with a speed v plus 2u. Do you understand that? In the frame of reference of the piston, the molecule is moving with the speed u plus v and bounces back with the speed u plus v. V plus u. Let's say v plus u. Makes more sense. V plus u, v plus u. But because in the frame of stationary frame of reference, this is moving with the velocity u, this is traveling with the speed v and bouncing back with the speed v plus u. Oh, Alexander, that's I'm glad to hear. Of course, if you need to go, you're welcome. So, does everyone understand? Do you understand on a scale of 0 to 10, please? Molecule bounces back with a higher speed. So temperature increases. Edith, how can I help you? How can I help you understand? So imagine you are sitting on the piston and you see a molecule and everything that is moving away from you with, like, imagine you're sitting on the piston. You are the piston, and the piston is moving with a speed 2, and the molecule is moving away from you with a speed 8. What is the speed relative to a stationary observer? If you're moving with a speed 2, and relative to you, it is moving away with a speed of 8, what's the speed? What's the total speed? 10, yes. It's moving away, it's moving at 10, because it's actually moving at 10, you're moving at 2, but in your frame of reference, you're moving with 0, you're not moving, and this is moving away from 8. So therefore, that's the real picture. That's the stationary frame of reference. That's why this is v plus u, but you're moving at the speed u, therefore it's v plus 2u. So the molecule gains energy from the moving piston. And if the piston is moving backwards, if the piston is moving backwards, then it's the opposite. It's v minus 2u. So the gas cools down because the particles lose speed as the piston moves back. It's like tennis. Look, if you play tennis and there's a ball and there's a racket, and if you hit it like that, it bounces back with a higher speed. But if you move the racket with the ball, like the ball is flying and you move the racket this way, the ball loses speed. Yeah, you can catch if you want to catch the ball with your racket, you move it backwards. But if you want to hit it back at a higher speed, you push it back. Okay. So yes, that's very important. Also, first reason is particles bounce from piston at higher speed. Second reason, well, you're doing work on the gas. You are doing work. And the change in internal energy is the heat plus the work done. And there's no heat, so delta U is W. That's it. That's an adiabatic process. An adiabatic process is a process that happens in a diesel engine. Diesel engines do not have spark plugs. Diesel is ignited by a fast compression of the piston. adiabatic compression, ignition, diesel. Here it is. So actually, is there a way to share the sound as well?
We can make it hot enough to ignite cotton.
Yeah, by
So, Nigel, what have we got here?
Can you hear it?
we've got something called a fire syringe.
And what does it do?
Oh, well, I'll show you what it does. Some cotton wool in there.
Okay.
I'm just going to compress the air in it, and hopefully it will. I don't know what it's going to do.
Wow.
That's pretty cool.
You made a spark in there. Was there any source of fire, like a match or anything down there?
Well, as you can see, it's pretty transparent. There was no match in there. It was actually just the compression of the air on top of it, which was able to ignite the cotton wool that we had in there.
So you're saying if we compress air, we can make it hot enough to ignite cotton?
Yeah, because air is made up of particles, so when you're actually compressing it, you're forcing those particles to collide closer together, which is actually going to raise the temperature in the inside of that tube there.
Okay, can you describe the apparatus for me?
Well, all there is there's a glass chamber in there where the cotton wool sits, and as you can see, there's this piston that moves up and down into that glass chamber, and as it moves up and down, you can actually compress the air.
So it's like a little plunger.
Like a little plunger, yeah.
Okay, so why don't we set one up so we can do it again?
Can I do it again? Okay, I'll clean the remnants out.
What are the tricks here?
The trick is to get not too much, but not too little cotton wool, and it's good to get it aerated so that there's a lot of air around it, so it makes it much easier to ignite, just like a good fire.
Is it just me, or do you feel like we're on a cooking show?
I feel like we're on a cooking show, yes.
Who do you think would be Jamie Oliver in this situation? Would it be you or me?
I'm more manly, so...
He's more like Nigella Lawson, let's face it.
That's a good play on words. I wish.
All right, we're ready for this?
Yes. Simple as that. Obviously no matches, no switches, no anything.
Okay.
We'll try it. Again?
You want me to try?
You can try it.
Yeah,
do you have the strength?
We're going to find out,
We'll find out. This is going to be awkward for Derek, I think.
Okay, so what I'm going to try to do is compress the air in there. And by compressing it, I'm going to increase its temperature because we're pushing all these air molecules together. And if I get it hot enough to the ignition point of cotton, hopefully the cotton will catch on fire.
Yeah, I've heard that the auto ignition temperature of cotton is about 400 degrees Celsius, so you can get quite enormous amounts of temperature from a very quick compression.
3, 2, 1.
Oh.
So yeah, that is the idea of a behind a diesel engine, and that's quite an ingenious situation. So you put some diesel into the piston of the engine of the car, and it compresses the diesel vapor very quickly. That increases the temperature. The diesel ignites and pushes back on the piston and does useful work. That's how cars operate. They so you compress the air inside the air diesel mixture, and yeah, that's there's no spark plugs in diesel cars. An adiabatic process is where there's no heat transfer, and therefore all change in the internal energy comes from the work. The diagram shows this process. Show that for such a process we have the following relationship. Okay, so we're gonna write the process. So du is dq plus dw. Now dq is 0 by the definition of the process, of the adiabatic process, and we have du equals dw. Now the work is the pressure times dv, but it's going to be negative because it is expanding. Yes, you can see AB is an expansion process. That means the work done on the gas is negative. So it's the gas doing work. So du is equal to minus P dV. Now we use the ideal gas equation, that P is equal to nRT over V. We plug that in. So du is equal to minus nRT dV over V. And then we can integrate. Oh yes, and we because we can use du, the formula that du is equal to CV dt. And CV dt. Now we divide by T because temperature is not constant. Minus nR dV over V. Yes, and now we can integrate it. We can integrate it from between limits. So we go from VA to VB, VA to VB, and this goes from TA to TB. Okay, so keep that here. So from here, we get, so if we integrate that, it's going to be CV logarithm T between limits TA and TB. And this is minus NR logarithm V between limits VA and VB. In other words, CV logarithm TB over TA, because we're subtracting logarithms, equals minus NR logarithm VB over VA. Okay, what can we do here? Well, we can take everything to the power E. So E, we're using the fact that if A equals B, then EA equals EB. And that works for any A and B. So E CV ln TB over TA equals E minus NR ln VB over VA. And that's going to be TB over TA to the power CV equals VB over VA to the power minus NR. Okay, and from here, we can say that, sorry, what do we need to prove? We need to prove that, oh, we've done it. Yeah, we can, yeah, we can remove the V. Okay, so we take everything to the power, So from here to the power -1, what is that? Oh, you can VA over VB is equal to, oh, to the power NR. Okay, I've switched them around, so it becomes plus, and this is TB over TA to the power CV, and VA over VB is equal to TB over TA to the power CV over NR. And I think that's what we need to prove. Yeah, that's exactly what we need to prove. All right, so that's the ratio. So this is a process. This is for an adiabatic process. Next one. We have two processes. Okay, so the gas begins in state A and ends up in state B. And there are two different ways of how you can get there. Can somebody identify the first process, this one? Let's call it C. AC. What is that process? What's the name of that process? Isobaric. Isobaric. Yes, isobaric. Is it expansion or isobaric contraction? Expansion. Of course, because the volume is increasing. CV. Use two words, please. Isothermic fixed. Isothermic cooling. All right, this is an isothermic. No, that's sorry, not isothermic. CB. Isochoric. Choric cooling. Isochoric cooling. And AB, what is AB process? Not BA, but AB. The temperature is constant. Isothermal. Thermal. It can't be cooling, so it's either thermal expansion. Expansion. Because you are expanding. Now, you could also call it isochoric depressurization rather than isochoric cooling, but that's not, depressurization usually implies you're losing gas, but this is not true. So you would normally call it isochoric cooling because what you're actually doing is you're cooling the gas rather than depressurizing it. If V2 is equal to 2V1 and both A and B are on an isotherm, show that P2 equals 1/2 P1 and TC equals 2T. Okay. Right, so what do we have? Well, let's consider AB. So P A. P1 V1 is equal to N R T1. This is for the first point, for A, at A. At B, we have P2 multiplied by 2V1, because it's double volume, equals nRT, and temperature is the same, so it's nRT1. Oh, that's interesting. So from here, it's quite easy. We can show that P1 V1 is equal to P2 2V1. V1 cancels, and we have P1 equals 2P2. Interesting. Also, like very simply, if it's a isothermic process, if the temperature is constant, then PV equals constant. If temperature is constant, then V. This is, by the way, it's the minute of it's Boyle's law. It's Boyle's law, of course. Right, so P1 is equal to 2P2. Then that's what we need to find. Well, we've shown that. Tc equals 2T. So at C, P1, because the pressure is the same, P1 multiplied by 2V2 is equal to nRTC, or T3. But we already know that P1 V2, sorry, P1 2V1. We know that P1 V1 is nRT1. So it's 2 times nRT1 is equal to nRTC. So nR cancels, and we have Tc is equal to 2T1. Here it is. Okay. Show by calculating the work done and heat exchange that the change in the internal energy is the same for the blue process and the red process. Okay, so for the blue process, so delta U in AC, delta U AC is the heat supplied minus the work done by the gas, which is minus the work done by the gas. So delta U AC is equal to the heat supplied minus in the process AC minus the work done in AC. And the work done is in AC is P1 multiplied by delta V. So 2V1 minus V1, which is QAC minus P1 V1. But QAC P1 V1, this is the amount of work done. Delta UAC. Doesn't say whether it's a monatomic gas or diatomic gas, but let's assume that it's a monatomic gas. And then for a monatomic gas, U is equal to 3/2 nRT. It's the the internal energy of an ideal gas. Therefore, the change, because the temperature goes from T to 2T, and that means delta U is equal to 3/2 nR2T minus 3/2 nRT, which makes it 3/2 nRT. So it's 3/2 nR. No, sorry, I can't use that. No. That's it. It says by calculating the work done. So no, delta U AC. Now the process, this is AC, and this now CB. In CB, delta U CB is equal to the heat supplied in CB plus the work done in CB. But the work done in CB is 0 because the volume is not changing. Therefore, it's delta U CB is equal to Q CB. So the total change, delta U in ACB, in the blue process, is equal to QAC minus P1V1 plus QCB. Okay, QAC, because it's an isobaric process, QAC is equal to CV and then, CP, CP 2T minus T. CP delta T, sorry. CP delta T, CP delta T, which is CP 2T minus T. So it's going to be CPT. Now the Q in CB, it's going to be CV delta T, which is CV T minus 2T, because the temperature goes from 2T to T. So that is minus CVT. But remember the first problem, we said that CP is equal to CV plus NR. CP is CV plus NR. We can use that. We can use that here. So QAC is going to be CVT plus nRT. And now we can apply this here. Delta U ACB is equal to QAC, which is CVT plus nRT minus P1V1 plus minus CVT. So CVT cancels. And then remember the gas law that PV equals nRT. P1V1, but P1 V1 equals nRT1, which is nRT. Therefore, the change of the internal energy in the process ACB is equal to 0. And it makes sense. The temperature does not change. That means it means that the internal energy does not change. Now, AB is an isothermal process. Yeah, so very simple. So in AB, delta U AB is an isothermal process, is equal to, well, you can use C. We can use du is equal to CV dt, but dt is 0. So that means 0. So at any point, the change in internal energy is 0. So that is 0 as well. So we've shown that the total change in the two processes, in AB, in ACB, is the same. So delta U ACB is 0, and delta U in AB is also 0. Okay. All right, I will finish here. I really hope you enjoyed COMPOS. And yeah, it was a great pleasure seeing you every week and answering your questions. And I really hope it was interesting to you as well. And well, I maybe see you in 2 years' time. Well, in actually a year and a half time, you can become our tutors. Right? You can become one of our tutors once you are in year 2 of university. And we are expanding. We are expanding to become bigger. We are planning to have over 1,000 students in the next 2 years. Yes, you as well. I wish you all the best in your university interviews if you haven't had yours yet, and your fulfillment of your offers, and set everything. You're welcome. Yes, thank you. See you soon. All right. Okay. See you. Well, hopefully not forever. Hopefully not forever. All right. All right.